And let me share the screen. So this is module 111 on AC. And oops, let me just. Okay. So, again, there's three approaches: ask questions, do it online, and do it by building and experimenting. So as we get along, I'll have more and more experiments going on. So we're going to talk a little bit about AC, DC, properties of AC, types of AC, and the uniqueness of AC. We've covered DC and Ohm's law and resistors in the past. Now, AC is a little bit complicated. This is sort of a quick overview of AC. We'll be going into a lot more detail on some of these topics, and some of the concepts are a little bit difficult to understand. I mean, I think it's important to realize that AC is different, it behaves differently, and it's got some uniqueness to it. Now, why all these things happen is a little bit difficult to explain sometimes, but we'll get into more details as we go on. So when we look at DC, it's basically the same. We have a circuit with a voltage source. Here it happens to be a battery with a resistor, and here we have a generator or an alternator or some sort of signal generator producing AC and a resistor. And the big difference is that DC is relatively constant with time. So if you hook a battery up to a resistor, it'll be around 12 volts until the battery drains or you turn off the circuit. Now, AC changes with time. So it starts off at zero, becomes positive, reaches a maximum, then starts going back down again, reaches zero again, then changes into a negative voltage, reaches a maximum negative voltage, and then goes back up to zero again. And typically, it's a sine wave, but there are different waves available. So when we talk about sources of DC and AC, so DC basically comes from a battery, which is a chemical reaction, a power supply, or a generator, which takes mechanical energy and produces it into DC. When we have AC, you need to have an oscillator, and that's like what a transceiver transmitter does in a radio. You can also have an alternator instead of a generator, and that produces AC. And then, for example, your heart also creates some waves. That's a chemical reaction, biological reaction happening in your body. Now, most of our electronics run on DC or some sort of pulses of DC. So why do we actually need AC? One of the things here is that it's required for distribution for long distances. So, you have a power plant, you have a step-up transformer, you run it along your transmission line, you get to a substation, then you bring it back down to distribution center, and you generally would lower down the voltage again with a transformer. And then here you have another transformer, bring it along to your, residential distribution system, and then you have another transformer here, which then brings it down, to your 120 and 240 volts. Up here, you could have 120,000 volts, 240,000 volts. I think there are even some lines going up to 750,000 volts. So you need AC for distribution. If we didn't have AC, we would all be living off of batteries, and we would have a completely different system. Some of the waveforms, typically it's a sine wave. You can also get a square wave, and this is what computers are using, except instead of having like a 50% duty cycle, they have a very small duty cycle. So you have little pulses going up and down, and this is what is used for your data transmission. You can have a triangle wave and a complex wave. So some of the things we're going to look at. So these are all the things that make AC different from DC. Frequency, voltage, current, phase, power factor, impedance, resonance, and transmission line. So we're going to cover briefly each one of these. Again, we'll cover these in more detail in the future. So one of the properties is since AC changes with time, so one of these cycles is called one wave or one cycle, and one cycle per second is 1 hertz. And here, for example, you have 3 cycles going by in a second, so that would be 3 hertz. And our AC is 60 hertz. And when we talk about frequency next, we'll talk about the whole range of frequency spectrum and RF radio frequency. So we have a number of cycles per second, which is the frequency, and then we can take the reciprocal of that, which gives you the period. So how long does it take for one cycle? And this we use for our band plans and frequencies, which we'll cover next week, and go into more detail how it relates to amateur radio. So for day-to-day transmission, it's usually 60 hertz. Some countries still use 50 hertz. And it typically uses a smaller wire, and it's easier to send across large distances than DC. Now, aircraft and military systems, they use 400 hertz. That allows them to use smaller motors and transformers. But it's difficult to transmit 400 hertz for long distances because of the inductance that's created. There's a big difference in inductance or reactance, inductive reactance, which I'll explain shortly, between 60 hertz and 400 hertz. So typically, you can only have a building running on 400 hertz. You can't really send it too far. And then audio frequencies are from 30 kilohertz to 300 kilohertz. And then radio frequencies are greater than 300 kilohertz. And we'll talk about band plans next week. So in an AC circuit, we have a number of additional components. So in a DC circuit, we have a resistor, but in DC, in AC, we have an inductor, which is like a coil or a motor, and then we also have something that's known as a capacitor. And we'll be spending a whole lecture on capacitors and inductors. So this is just an overview of what's happening. So it's a lot more complicated. And these also react in DC, but in AC, it becomes more complicated. So one of the things we'll talk about is power factor. We won't get into a lot of detail about this, but basically, if you look at this, when you're getting electricity from hydro, you're paying for the mug of beer. And when you go to drink the mug of beer, you have real power, which is the liquid, and you have the reactive power, which is the foam, which is basically wasted electricity. And you get this difference here because of the inductance of all the motors and transformers in the system. So what you want to try to do is reduce the amount of foam as much as possible so you get the real beer. And you can do this by putting capacitors into the circuit. So this is one example, and if you get into electrical engineering, they'll talk a lot more about this. So this is one of the differences of AC and DC. The other thing is that the voltage is different, and since it changes with time, you need to have some sort of equivalent to DC. So what you have here is if you look at the voltage on an oscilloscope, you get voltage peak to peak. And then if you divide that by 2, you get voltage peak. But if you now look at the amount, if where there is no voltage, and sort of flatten this out so it acts more like a DC voltage, it becomes 0.7 of the V peak. And this is known as VRMS, or root mean square. So this is the value that you're usually measuring on an voltmeter or a VOM or digital meter. If you're looking at it on an oscilloscope, you'll get V peak to peak. So that's another difference. So here are some of the calculations. Basically, it's 1 over the square root of 2. That makes up the difference, and this is the equivalent. So if you had a resistor and you were running DC through it, you would need this amount of voltage. If you were running AC through it to produce the same amount of heating in the resistor, you would need VRMS. So, for example, when we measure 120 volts coming out of our outlet, it's VRMS. But if you did the calculations and you came up to V peak to peak, you would end up something like 340 volts. So this is important then if you're planning for capacitors or resistors. You want it to be able to handle at least 340 volts, not just 120 volts, which is what you measure on the meter. So as I've said, an oscilloscope measures peak to peak or V peak. Nowadays, the oscilloscope will do all these calculations for you. Multimeter is VRMS, but one of the things you have to check is if you're measuring other frequencies than 60 hertz or others than a sine wave, your multimeter may not give you the right value. And there are some multimeters that are called true VRMS multimeters that are supposed to work on a number of different frequencies and waveforms. But again, those are more expensive, and normally you don't need those. So the other thing that is somewhat difficult to understand is that you now, when you pass current or voltage AC through like a capacitor or resistor, you get now a difference between the voltage and the current. And the difference between the voltage and the current is known as phase. And also if you, for an amateur radio, if you have two signals and you want to modulate it, you can also phase modulate it by moving this back and forth. And it's similar to FM modulation, and we'll cover that again in the future. So the phase is basically the measurement, the difference between two waveforms. So there is this expression called Eli the Iceman. So, if you have an inductor, which is basically a coil, the voltage leads to current. And if you have a capacitor, the current leads to voltage. So they came up with this expression, Eli the Iceman, so you could remember it. And then if you were to look at it on the oscilloscope, you would actually see a difference between the voltage and the current. And when we talk about inductance and capacitance, we'll try to demonstrate this on the oscilloscope, so you can see the difference in the waveforms. So we'll cover this again. And then, one of the things with AC is now when you have capacitance and inductance in the circuit, it's now known as reactance. And you have inductive reactance and you have capacitive reactance. And you now introduce a new component called impedance. And compedance is basically reactance and resistance combined, but it's not a simple addition. it's all based on trigonometry, and so basically it's the Pythagoras theorem. And to calculate this on this vector, it's basically the square root of the sums, the squares of the sums. But you don't need to know this. We'll in the advanced course we'll be covering some of this, but this is just to show you that it becomes more complicated, and the capacitance reactance and the inductive reactance cancel each other out. And this is, for example, what you do on an antenna tuner. Is you see what the capacitance reactance is and match it with an inductor, or see what the inductive reactance is and match it with a capacitor to cancel this out, and then transform the impedance so that it matches the output impedance of your radio. And again, we'll cover this in more detail. One of the things is that in the advanced course you'll be expected to do some of these calculations. So to do capacitive reactance, to calculate that, it's basically 1/2 pi f, which is the frequency, and c is the capacitance. And then the inductive reactance is calculated by 2 pi frequency plus the inductance. And again, we'll cover this when we do inductors and capacitors, just a preview. And so what happens is when you look at the inductance, it generally increases with frequency, and the capacitive reactance goes down with frequency. And where these two cross is the resonance point where these two cancel out, and that's what you're doing with your antenna tuner. And so on the basic exam there'll be some questions about this point. What happens to current and what happens to the voltage. So we'll cover that when we do the circuits. So one of the uses of resonance is to generate oscillators. We'll talk about oscillators in the advanced electronics course, but we'll cover filters in the basic course. So by putting together various capacitors and inductors, you can get a low-pass filter, which just allows the low frequency signals to come through. You basically have frequency on the bottom and attenuation at the top. So low frequencies go through, and then the higher ones are stopped. And then you can also have a high-pass filter where the low ones are stopped and the high ones go through. And then you can have a bandpass filter which only allows a certain band to go through. And then you can also have a notch filter, which is just the opposite. So it allows things to go through and then doesn't allow this signal to go through and then allows this to go through again. So you use these filters to tune in your radio, different stations, and eliminate noise and the interference. And we'll be covering some of this in more detail when we get to the RLC circuits and how they actually work. So one of the things here is use of impedance is to match the antenna to the transmitter. And so usually the transmitter or transceiver is at 50 ohms, and the antenna can be higher than 50 ohms or lower than 50 ohms. And then you have a transmission line in between them. And the transmission line or feed line is usually 50 ohms also, but can be 75 ohms. 75 ohms was quite common for TV and also closed circuit TV. And then the antenna can range from 25 to 5,000 ohms, and it depends on the antenna type. When we talk about antennas, we'll talk about impedance, and it also depends how high your antenna is off the ground. So you want to match this so you get the maximum signal going out of your transmitter. One of the things is wire length becomes important as you go up in RF frequency. And typically you want to keep your wire lengths, if you exceed 1/10 of the wavelengths, you start to run into problems because your wire also acts as an antenna and has capacitance and has inductance, and all these components react with one another. When you get into RF, neatness doesn't necessarily count. So sometimes you can build this circuit and have like nice holes going through here, and have the capacitors all nicely mounted on the board, but then the circuit doesn't work. And you just put something like this together and it works much better. So there's an art and science to RF, and nowadays they have computer simulation programs for how to design circuit boards, and they calculate all of these things automatically. One of the other things I wanted to bring up is transmission lines. Um, so if you go back here to your transmitter receiver and you have a feed line, typically you have your transmitter receive switch built into your radio, and you just connect the antenna here with a UHF or a BNC connector, and then you have a feed line going up to the antenna. Now if your feed line happens to be resonant to a wavelength of the frequency you're using, you might get strange things happening. So if it works on some bands but doesn't work on another band, it could be because your feed line is resonating on that particular frequency, and you may want to try a different length of line to see if you get a different result. And just to introduce this, it's a little bit uh, if you have a feed line like a coax cable, and you look at the end, you have a couple of things happen. One is that your signal will go down the line, and if you're matched, it won't go back. But if it's not matched, it'll start to reflect back and then keep on going back and forth. And this is where your SWR gets uh, it's basically a ratio of the maximum voltage to the minimum voltage. That'll give you your SWR. And we'll talk about that when we talk about feed lines and antennas. But another interesting thing that happens is that if you happen to be on the resonant point of, let's say your antenna, you're operating 10 meters. So your lambda is 10 meters. So if your feed line happens to be 5 meters, or 1/4 of that, or 3/4 of that, then you can get strange things happening. So in this case here, if your line is open, then depending where you are, it can actually look like a short. It could either look like being open, or it could look like being a short. And then if your line happens to be shorted out or low impedance because of the antenna, it can have the opposite effect. And it can appear like an open line or a shorter line at these various um, parts of the wavelengths. So if you're having problems with your antenna, try a longer antenna or a shorter antenna, and we'll try to do some of these experiments with 70 centimeters and 2 meters, and try to set something up so you can actually see this effect, because this is quite unusual for a transmission line and for AC. What we're going to try to do is put a light bulb at these various points on a line, on a straight piece of like ready rod, and you'll see the lights will light up at one point and then won't light up here, and then light up here again. And if you were running DC through the line, you would get your light bulb would light up regardless of where you would be. So this is another property of AC and transmission lines that's quite interesting. And why it happens is that you know, you have a combination of capacitors and inductors in the line and between various components. So, you have these in parallel, and you have, just the capacitor by itself, and then you have them in series, and then you have the inductor by itself, and then you repeat this sequence over again. And depending on what your resistance, your inductance and capacitance is, will tell you what sort of things will happen in the line. And you for transmitting to generate RF waves at your antenna, you typically want maximum current. You don't want maximum voltage. So if this, like for example, this like a dipole antenna, and if you looked at the curve of the dipole, you would have maximum current at the center of the dipole and maximum voltage at the ends. That's why you have an insulator there. And that's why they say, keep away from the ends, because you can get a shock. It could be several hundred volts here, but most of your radio signal is coming out the center of your dipole. And we'll talk about this when we get into antennas. So another interesting thing is about conductors. And if you have DC, it travels typically on the inside of the wire. Now, you have a thing called the skin effect. And the higher the frequency, the more of the skin effect you see. So the RF signal actually travels more on the outside of the wire than inside of the wire. And the other interesting property here is if you have a coax cable, most people think it's two conductors. You have the center wire, and then you have the shielded braid. And you think, oh yeah, I've only got two conductors. But what actually happens is you actually have three conductors. You have the center wire, you have the inside of the shield, and you also have the outside of the shield. So RF can run on the inside and on the outside. And you want to try to keep the RF on the inside of the shield, not on the outside of the shield. So you can have things like RF in the shack and common mode current, where you get things running back into the shack and then getting your electronics behave strangely, like your computer acting up every time you transmit, or your antenna tuner not working sometimes, and you can't really explain it because it's RF going back into the shack. So there are things we can do here, adding a choke or a transformer or a balun to eliminate some of these things, and we'll explore all these things when we get to antennas and feed lines. So when we look at AC, again, we have a resistance, which is same as in DC, but now we have things like an inductor or a capacitor in the circuit. And there's a number of different ways of looking at it. I don't want to get into a lot of the details, but if you look or Google AC, you can come up with a whole lot of information. And you can come up with an impedance diagram where you get these formulas here, and it's shown this way. And then you can also get a phasor diagram where you start getting into angles, and it's shown this way. And then you can look at the waveforms and see where they are, and you can actually have like mathematical um, formulas for a sine wave, and calculate what the mathematical formula is for the voltage and for the current, and then divide those sine waves. So I mean, there's a lot of mathematics involved if you want to study that. But we're just interested basically in this diagram here, and how to look at how some of these things happen. And we're not going to get into the mathematics, but all of that is available if you have a keen interest in studying AC. And again, don't worry about the details, just realize it's different. And when we cover sections on inductance, capacitance, reactance, impedance, resonance, filters, antennas, feed lines, and transmissions, we'll go over this in more detail, and I'll have some experiments set up where I can actually show you some of these effects of of AC going through some of these components. So any questions on that? Let me just stop the share and turn off the recording.